Okay, section 17, linear regression. So we've talked a little bit about correlation and scatter plots, and now what we want to do is talk about finding the line that best fits the dots. So this is a little vague, but we'll specify exactly what we're talking about as we go on. But notice, however, that as I said in section 16, when you're talking about correlation, we're not making any kind of distinction between which variable is which. The correlation between tissue boxes and hot chocolates is exactly the same number as the correlation between the other way around, whichever way I just said it. So remember, correlation measures how lined up the dots are, and if you do a physical flip this way, so that tissue boxes are horizontal and hot chocolates are vertical, it doesn't really change how lined up the dots are. So the correlation, let's try again, the correlation between hot chocolates and tissue boxes is exactly the same number as the correlation between tissue boxes and hot chocolates. However, when you go to draw the line that best fits the dots, you want to understand what the purpose of it is. The purpose is to do some predicting. So for instance, if this is the line that best fits these dots, then it would go through about here, right? So if you had a month in which you sold 40 hot chocolates, you would predict, what, 250-ish tissue boxes being sold. Now these predictions are only going to be as good as how lined up the dots are in the first place, but we'll talk about that a bit later. The point is, we want to do some predicting, and the minute you're doing predicting, you are making a distinction between what you're predicting with, in this case the hot chocolates, and what you're predicting, the tissue boxes. So now we are definitely making a distinction in this section between which variable is which. Let's take a less obvious example of the weekly TV hours and the GPA. Let's say for the sake of argument that the line that best fits these dots runs something like this. Then horizontally, if you're around 21, you'll be about here, right? Now remember, you can have dots above and below other dots. There's no reason you couldn't have two students with the same TV hours and different GPAs. But you're only going to have one height of the line there, which is about where I have the cursor. So you can see how this plays out. The reality is up there at 3.5. The prediction is down here at maybe 2.5. So if the dot is very far away from that best fitting line, then the predictions are going to be pretty lousy. You can see that the height of the line, where the cursor is, and the height of the dot, they're very different. That vertical distance is very big. On the other hand, if you've got a dot that's close to the best fitting line, let's say here at maybe 14, then maybe you're predicting, I don't know, 3, but the reality is 3.1, slightly above it. You got a dot close to the line, the prediction is pretty good. You got a dot far away from the line, the prediction is pretty bad. Now, if all the dots are close to the line, then of course the worst prediction, which is maybe here, is still going to be pretty good. But if the dots don't form a line quite so tightly, if the correlation is a little lower, then some of the predictions will be reasonably close, and some of the predictions will be very far away. So this gets us a little closer to what we mean by the line that best fits the dots. We want the line that will predict better than any other line will predict. Now let's think about this. How far off your prediction is are these vertical distances from this theoretical best line, or any line that you're trying to predict with. So how can we quantify that? Let's say height of dot minus height of line. Well, if that's the way you do things, then of course this is going to be a positive number. On the other hand, height of dot minus height of line, this is going to be a negative number. So you can see that we're going to get some cancellations going on here. Also, let's point out the obvious. If we want to make all of these predictions good, well, there's going to be trade-offs involved, right? If I want the line to run through this dot so that that prediction is perfect, then maybe it'll go something like this. And look what happens by the time we're way up here. Trying to accommodate that dot, trying to get the line running through that dot, makes all these dots over here further off. So there are going to be trade-offs. They're a little more obvious over here, of course. If you want to have the line running through this dot, then, or closer to this dot, then of course it's going to be a lot further away from all the other dots. So there are trade-offs involved. We would like collectively, we will call the line that best fits the dots for our purposes, the line that predicts better than any other line would predict. To get a little closer to it, what we're looking for is the line that makes these vertical distances collectively smaller than any other line would make them. But again, there are trade-offs here, and trying to make one of those vertical distances smaller is making others bigger. So how do we cope with that? Collectively doesn't quite cut it. Well, we could add them up. But again, the problem is some of them are going to be positive and some of them are going to be negative. So if you add them up, you're going to start getting cancellations, and in fact, you always get 0. So that's not going to work. Well, lose the sign and add them up. We've tried this before. We tried it with standard deviation S back in section 2, and losing the sign, absolute value, turns out to be a little mathematically troublesome. It turns out that's not the easiest way to lose the sign on things. It turns out it's easier to square things if you want to lose the sign. And that's basically what we did. So let's recap. We'll do that again. By the line that best fits the dots, what we're going to mean is the line that makes collectively the squares of these distances smaller than they would be for any other line. And now by collectively, because they're not negative, I can just mean add them up. So the line that best fits these dots, what we'll mean by it, is the line that makes the sum of the squares of all these vertical distances between line and dot smaller than they would be for any other line. And that's why we call this the least squares regression line of y on x. Now again, y on x definitely makes a distinction between the one variable and the other. The least squares regression line of hot chocolate on tissue boxes is not the same critter as the least squares regression line of tissue boxes on hot chocolates. If you think about it, because we're flipping the picture inside out, that would be making the horizontal distances as small as possible. That is, it may be close, but it may not be necessarily exactly the same line. You'll see a bit of a difference. And if they're not very lined up, you may see a major difference. So we definitely make a distinction between which variable is which. The least squares regression line of what you are predicting on what you are predicting with is the line that makes the sum of the squares of the vertical distances smaller than they would be for any other line. And that's what we'll mean by the best line. So that quantifies what we're trying to achieve a little bit. We're not going to prove how we get these formulas, but it at least explains why the formulas are what they are, because you want the line that will predict better than any other line will predict. And having established that, you're making a distinction between what you're predicting and what you're predicting with. So with all that in mind, we want to be a little careful about our terminology then. Because we are making a distinction between the two variables, the explanatory or predictor variable is the one that goes in, the one you're predicting with. And the response variable is the one that comes out, the one you're predicting. Remember, there is not necessarily, you want to avoid the word cause. In no sense does buying a lot of hot chocolates cause you to buy more tissue boxes. Yes, maybe there's a causal relationship there, but it is indirect at best. Forcing people to buy hot chocolates does not magically make them want to go out and buy tissue boxes. And it certainly doesn't work the other way around either, so we're not thinking about it backwards. You want to avoid the word cause, but nevertheless, you may be able to predict. You may be on somewhat solid ground if you said, okay, if I sold 40 hot chocolates this month, I would sell about 230 tissue boxes. Predicting puts you on somewhat solider ground than causation would. Now, these words are a little bit loaded. An explanatory variable explains changes in the response variable. That's a bit tautological when you think about it. And the word explain is not necessarily very helpful, but the point is that we are trying to do some predicting. We are not necessarily assuming any causal relationship. And as I talked about in the last video, you definitely want to make a distinction between the data you happen to have and how things would play out for all possible months or for all possible students. You never know whether the data you have is cherry-picked. I mean, if you've got a random cloud of dots here and you erase enough of them, then what remains are these dots that are lined up. You can always cherry-pick data. That doesn't necessarily prove anything about the real world. So you definitely want to make a distinction between the data you happen to have and all possible data. We're not going to do any inference here. We're not going to do anything like hypothesis tests. You can do them, but we're not going to get to them in this course. So we are going to be a little bit less ambitious in our aims here. We're just going to talk about predicting from the data we happen to have. Whether or not those predictions are sound is a little bit beyond mathematics, at least beyond what we're going to be looking at. The point is you're definitely making a distinction between which variable goes in and which variable comes out. The explanatory variable, the one you're predicting with, that's the horizontal one, call it X. The response variable, the one you're predicting, the one that comes out, call that Y, the vertical one in the picture. We're not going to focus on the pictures necessarily, they're just a visual aid to understand the concepts of the formulas. But X, horizontal, input, explanatory variable, Y, vertical, output, response variable. That's how we'll organize our terms. Also, if you are talking about the line that best fits the dots, then you are making a distinction, of course, between the dots, the realities in blue, and the predictions, the red dots which constitute the line in red. So again, the predictions are the red dots that make up a line. The realities, which may or may not be going through those dots, are the purple. The realities in purple, I think I said that wrong, but the realities in blue, the predictions in red. The predictions, of course, are a line. So the realities, the blue dots can be close to the red line, or they can be far away from it. That's just a consequence of how high correlation is. Correlation, remember, measures how lined up the dots are in the first place. You can always predict. How good the prediction is remains to be seen, but you can always predict. You can predict well. Worst case scenario, this prediction is not so great. Or you can predict not so well. These dots are not that close to the line in all cases. So we'll talk about how valid the predictions are a bit later, but you can always predict. That is to say, you can always find the least squares regression line. You can always find the line which will predict better than any other line would do, in the sense that it makes the predictions at those horizontal locations closer to the dots, vertically speaking, than they would be for any other line. To say this is the least squares regression line in this case is to say that these vertical distances, the sum of the squares of these vertical distances between dot and line, are smaller than they would be for any other line. And a little less formally is to say that for these horizontal locations where we happen to have dots, this line is predicting better than any other line would do. Now again, strictly speaking, we are talking about the data we happen to have. So this line predicts for these dots better than any other line would do. Anything after that is a bit inferential, and we'll talk about it later. But if you're talking about how this line is constructed, it's constructed so that these particular dots will be predicted as well as possible. Also, because we are talking about predictions, not realities, when it comes to the heights of the red dots that make up the line, remember, hat is a symbol in statistics that means predictor of. So when we're talking about the predictions, the red dots, the line, we're talking about y hat. The realities are the y's, the blue dots. Well, from pre-calculus, you should probably know that the equation of a line is y equals mx plus b, where m is the slope of the line and b is the y-intercept. The y-intercept may not necessarily be meaningful because we're not starting horizontally at 0 necessarily here. You could be talking about temperatures and starting at less than 0. So this vertical line is not horizontally at 0. It's at like 19 something. But nevertheless, it's mathematically present in the formula, and we can compute it and get on with things. Bottom line, if you got m and b, then you can plug in an x and get out a y and do some predictions. So quantifying the least squares regression line is not necessarily graphing it for us. You could graph it. We're not going to necessarily, but at least finding the m and b. You have the line if you have m and b. So we want a formula to find m and b. M is the slope of the line. Remember, correlation is not slope. It's related to slope very superficially. Positive association, that is to say, the line that best fits the dots will go up, means a positive R, negative down. But that's where the similarities end. Remember, the numerical aspect of R is not anything to do with steepness, but rather how lined up the dots are, which is a different critter. So correlation, which was an end in itself in section 16, is now a step along the way for further calculations. So you want to have a fair degree of accuracy for it if you're going the extra mile here. Now, I'm going to assume that you've computed correlation the way we've computed it in the previous section. In other words, that you found the 5 underlying quantities, the sum of the x's, the sum of the y's, the sum of the x squares, the sum of the y squares, the sum of the pairs. Then you constructed the 3 major pieces, SSX, SSY, which is same thing with y's, and SSXY, and from there you found correlation. So in other words, if you've done that, then these are the pieces you've already computed. Most books will tell you that correlation is that m is r times the standard deviation of y over the standard deviation of x. Now, strictly speaking, we don't have those handy, although if we have SSY and SSX, they're only a divide and a square root away. But you can put all that together into the same formula and do some cancellations, and it ends up just being this. So in terms of the pieces we have, the way we've computed correlation, m would be r times the square root of SSY over SSX. This is very easy to remember. First of all, notice that it makes a distinction between which variable is which. As I said, y divided by x is not the same thing as x divided by y. We didn't see anything like that in the correlation formula. Linear regression cares which variable is which, but it is very easy to remember. Y is on x in the grammar. Y is physically on x in the picture. And y is on x literally in the formula. So in every sense of the word, what you're predicting, y, is on what you're predicting with x. Very easy to remember. So we found SSY, we found SSX, divide them, square root. We found them in order to find r, so we've got that too. Multiply. We got m. Now as far as b goes, we'll just back substitute. So b is y minus mx. But the question arises, which y and which x? The first xy pair, the last xy pair, the middle one? We'll split the difference. We'll use the means. So to find b, we'll use the mean of the y's minus m times m being just found, the mean of the x's. Now again, you may not necessarily have the mean, but you're only a divide by n away. If you have gone through correlation, then you have the sum of the x's and you have the sum of the y's. So to put it in terms that may be a little easier, it's the sum of the y's divided by n minus m times the sum of the x's divided by n. Same thing said another way. Okay, now you've got m and you've got b, so you've got your line. You've got y hat equals number times x plus number. You've quantified the least squares regression line, and now you can plug in numbers and actually solve things. So that's the theory, basically. We'll do the examples in the next video. Some concluding remarks. I think I've talked about most of this already. There is nothing symmetric about the above formulas. If you want to reverse this, having talked about the least squares regression line of height on age, if you want to go back and do the least squares regression line of age on height, then you literally have to start from scratch. There is no easy reversal here. Turning the formulas inside out will be a disaster. So my advice is to stick to calling x the thing you're predicting with, and stick to calling y the thing you're predicting. In other words, having found the least squares regression line of tissue boxes on hot chocolates, to predict tissue boxes from hot chocolates. If you then wanted to go back and do things the other way, if you wanted to predict hot chocolates from tissue boxes, if you wanted to find the least squares regression line of hot chocolates on tissue boxes, which remember amounts to a visual flip, then what you will do is, real world distractions here. What you will do is relabel. If you want to predict hot chocolates from tissue boxes, if you want the least squares regression line of hot chocolates on tissue boxes, then call this one y and call this one x. In other words, it is easier to relabel the concepts than it is to turn the formulas inside out. Always stick to calling the thing you're predicting with y and the thing you're predicting x. Okay? So that's the theory, and we'll talk about the examples. We'll continue on with the examples we've previously discussed in the next video.